Hello, I hope this video finds you in good health. This video concerns itself with the process of integration by parts, which is required whenever we have two functions of x multiplied together. The formula is the integral of u dv by dx equals uv minus the integral of v du by dx. Unlike the product rule, we have to make a decision. We need to assign one of the parts to u and the other to v dash. This means that we need to differentiate the one we assign to u, but integrate the one we assign to v dash, and whatever we choose to do, we have to be able to integrate the vu dash. Before embarking on a catalogue of examples, I would like to offer some suggestions to make our journey less bumpy. Suggestion number 1. If we have x multiplied by a function of x, let u equal x and v dash the function of x, unless the function is ln x, in which case u equals ln x and v dash equals x. Note that x to the n sin x will require n applications of integration by parts, but x to the n ln x only requires one application. Suggestion number 2. If we just have to integrate ln x, we put u equal ln x and v dash equal 1. And suggestion number 3. For a function like e to the x cos x, we put I equals e to the x cos x and apply the method twice, making sure we apply it consistently. That's enough suggestions, let's get cracking. We've got 5 splendid examples. I'll see you at the other end. We begin with example 1, the integral of x e to the 3x dx. As I mentioned in the first of my suggestions, I've put u as x, so u dash is 1, and v dash is at e to the 3x, so that v equals a third of e to the 3x. Then we substitute into the formula. uv is a third of x e to the 3x, and we subtract the integral of the vu dash, the products of the two things we didn't start with. Integrating e to the 3x is simpler than integrating x e to the 3x, so I made the right decision. Why, thank you. The final answer in the bag. Now for example 2, which is related to example 1. The integral of x squared e to the 3x dx. I've gone for u as x squared, so u dash is 2x, and v dash equals e to the 3x like last time, so v is a third of e to the 3x. Applying the formula, we get a third of x squared e to the 3x minus 2/3 of the integral of x e to the 3x dx, where the thing we need to integrate is what we had to integrate in example 1. So because we had x squared, we had to use the method twice. Simples. Cast your mind back to my suggestions. When the function is ln x, we put u as ln x and v dash as the power of x. So, it's example 3, and v dash is x to the 5. U dash is 1 over x, and v is a sixth of x to the 6. When we multiply 1 over x by a sixth of x to the 6, we get a sixth of x to the 5, which is easy to integrate. Job done. Example 4 is a classic, the integral of ln x. At first glance is only one part, but that's because we used the number 1 for the other part. U equals ln x, so u dash is 1 over x again, and v dash is 1 with v equal x. So we get x ln x minus the integral of 1, and what could be easier than that? No need to answer, it was a rhetorical question. Lastly, and possibly most intriguingly, example 5, the integral of e to the x cos x. No polynomials here to worry about, and in fact you could choose either e to the x or cos x as your u. I've picked u equals e to the x because someone had to, and you're just watching. So, u equals e to the x, so does u dash, v dash is cos x, and v is sin x. Stick it all in, and we get e to the x sin x minus the integral of e to the x sin x, which makes it look like we haven't achieved anything. Do it all again, consistently, using u as e to the x again, and we get e to the x sin x minus, brackets, minus e to the x cos x minus integral, minus e to the x cos x. And again, at first glance, it looks like we're back to the beginning, but now for the smart bit. We call the thing we were asked to find I, and that gives us I equals e to the x sin x plus e to the x cos x minus I, whence 2i is e to the x sin x plus e to the x cos x, and I is half of e to the x sin x plus e to the x cos x. Thank you very much for watching.